Bismillahirrahmanirrahim. Assalamualaikum and good morning. So we move to chapter 2, guys. Okay, PID controller design. So we left chapter 1, the rule of root locus technique. Okay, for time domain design. So in this chapter 2, I will talk about some revisit to time domain analysis, design with gain adjustment, improving the steady state error, which is a PI controller. So this is the borderline for test 1. Okay, so until PI controller. And then we go to the improving the transient response. Improving the transient response using a PD controller. Then improving transient response and steady state error together using PID controller. And then we go to the Ziegler-Nichols PID tuning method and some computer program using MATLAB. So as we all know that root locus is a tools. Okay, in fact, is a powerful tool in the design of controller in time domain. So it have 4 type of controller, which is gain adjustment, usually known as P controller. Okay. Second one is the PI controller to improve steady state error or to reduce steady state error become 0. And then PD controller, proportional derivative, which is used to improve transient response from slower become faster. And then PID controller, which will improve, to reduce error and at the same time to make the response faster. Okay, together simultaneously, 2 in 1. And in order to do PID, we need to do tuning, okay, to find the suitable value for the constant proportional, constant integration, and constant derivatives. Okay, we call it as Ziegler-Nichols tuning. As you know that for any control system, we have a lot of input, okay, impulse, step, ramp, parabolic, and sinusoid to design the controller. So usually we use a step response, which is the square wave, okay, as the input of the system. As long as others as well, which is a ramp and parabolic, okay. For sinusoidal, we apply this one in frequency domain. So you know already that when I talk about poles, can be open loop, it can be closed loop, okay, which is the denominator of transfer function, either open loop or closed loop. Okay, and the symbol is cross. Zeros is the roots of the numerator of a transfer function, either is this open loop or closed loop. Okay, and the symbol is 0. And poles and 0 can be mapped on S-plane, okay, together using a S-plane, okay, where we map the poles and zeros probably over here, over here, over here. And this is, we call it as a PZ mapping, okay? Poles and zero mapping on S-plane. And we know that every model have a transfer function. Okay, the output over input. This is a sample of a first order system, where first order system, definition of first order system is the system that has single pole. Okay, so please remember, when I ask you what is the first order system, the answer is first order system is a system that has a single pole. Okay, one pole. Let's say minus A, and it's located at the denominator of the transfer function. So this is the frequency domain transfer function. So when we inverse Laplace, okay, so we will get the expression of the output in terms of time, which is 1 minus exponent AT if we give step input 1 volt. Okay, 1 volt peak to peak. So this is the equation of the 1 over exponent minus t, okay, where C of t is equal to 1 minus exponent minus AT. You can see the time response is rising from 0 to the final value, okay. Final value is about 1 volt, okay. And in first order time response, some information hidden can be extract out, okay. For example, time constant, which is tau, okay. So tau is the time constant where it occurred at the 63% of the final value at t, okay. For example, here, if the final value is 1, okay, final value is 1, so 63% multiplied by 1 volt, you will get Yongsheng. 63% multiplied by 1 volt, you will get, tak datang,
0.63.
0.63 volt, okay. So around here, so the correspondent time is here, which is 1 over A. Okay, so once you get the time constant, so the rest we can know, which is the rising time, which is 2 over A, and settling time, which is 4 divided by A. Okay, so please remember the formula that is correspond. Hello, siapa tengok video tu? Karen. Time constant, which is 1 over A. Rising time, which is 2 over A. And settling time, which is 4 divided by A. What is A? A is the poles value. Okay, guys? Poles value. So please remember these three formula for first order system. Then we move to the second order system, as you learned last semester. Okay, where the transfer function is given by omega n square over s square plus 2 zeta omega n s plus omega n square, where omega n is the undamped natural frequency, okay, and zeta is the damping ratio, okay. So the second order system response are determined by the damping ratio value and the natural frequency value. And it can be categorized as overdam, underdam, undam, critical dam, and negative dam based on the damping ratio and pole location. So this is a standard second order system. Okay, where you find the roots as a poles value. Why we call it as a second order system? Because system has two poles. Okay, so S square, when you find the roots, you will find two values of roots where it represent the poles value of the system. So the first category of a second order system is known as overdam. Okay, overdam is where the zeta value is greater than 1. And the location of the poles are on the left hand side, left half plane, where the value is real value, real different real values. Okay. So why I call it real? Because it's minus 7.854 and minus 1.146. It's not integer number, it's a real number. Okay. And the response is approximately like this. The output response, the input response is square, and the output is something like this. Second one is the underdam, which is between 0 and 1. Okay. And the nature of the poles is complex conjugate poles, which is one pair, which is a minus 1 plus minus j square root 8. Okay, one at the top and one at the bottom. And this is the most response that we want because it is operated on the left half plane, or usually known as underdam region. The area that I always tell you many times. Okay. The third one is undam, where zeta is equal to 0. Okay. Meaning that no dam, and the location of the poles is plus minus J3, where only imaginary number. Okay. Imaginary number and no real. Okay. No real part. And the response is oscillations. Okay, this one we call it as the oscillation response. Okay, it's a swing from 0 towards the infinity. The third one is critical dam, which is where zeta is equal to 1. Okay, and the nature of the poles is left half plane, but overlap each other. Okay, same value, overlap each other. Okay. So what is the next one? The number 5, negative dam. Negative dam. Somebody told me negative dam, Amir Nur Farhan.
Yes,
Amir,
Doktor.
example of transfer function. Uh, negative than 9 minus 6s plus 9. Okay. So find the roots. Amin or Farhan, find the roots. S square minus 6s plus 9.
S equals to 3, Doctor.
S is equal to
Negative 3.
kalau plus 6s plus 9 is minus 3 minus 3. This one is
Eh, uh, S equals to 1 plus minus set 2 AJ set 2.
ini kan melalu dah. Cuba tengok kan dia punya zeta tu negatif. Find the roots 6s square minus 6s plus 9.
Positive
Split.
3.
Ah,
Positive 3.
3, 3.
Yes.
And we check with the MATLAB. S square minus 9s. Wait, I share with this. Okay. P equals to 1 minus 6, 9. Can you see what I type?
Yes, Doctor.
Yes, Doctor.
Roots P. Okay, so you find the positive 3, eh? Correct? Positive 3, positive 3. Which is kan sini eh. So the location of the poles is on the right half plane. Guys, right half plane, unstable. Okay. And what is the shape of the response? When Hui, what is the shape of the response for negative then? When Hui tak datang.
Ada.
Nah, cakap panggil nama tak dengar, tak datang. When Hui, mana?
Ya.
Negatif then. Shape. Tak tahu.
Right.
Dia dekat bawah.
Kat bawah mana? Bawah meja. Bawah katil, bawah meja. Dia bukan kat bawah. Dia berayun dan membesar. Is oscillation and becoming bigger when t towards infinity. Macam tu kan. Bukan dekat bawah. Bukan dekat bawah katil, bukan dekat bawah meja, bukan dekat bawah kursi. Okay. So add that. Negative them. Negative them, what is the range? I mean, Hui? Zeta? Range of zeta?
Yes, doctor.
Range of zeta for negative them.
Less than 0.
Less than 0.
Less than 0. Okay? Less than 0. Okay. So this one, there is no negative then response, so you can just add. When times towards infinity, the response becoming bigger and bigger. Then dia burst, meletup. Boom, unstable. So this is the second order time domain spec where we have a C maximum, C final, okay, 1.02 C final, 0.98 C final, and 0.9 C final, and 0.1 C final. This is to indicate the rising time, okay. So rising time is T 90% minus T 10%. Okay. Peak time is when the response at C maximum. Okay. So that is your peak time. So settling time is where PS is plus minus 2% of the final yearly. Right? Which one comes first? Either 1.02 or 0.98. So in this case, 0.98 comes first. So this is your settling time. Sometimes the 1.02 comes first. It depends on the situations. Okay, so that is your settling time. And we can simplify using the formula, okay, which is peak time is Tp plus omega d. Okay, this is omega d. This one is omega n. So what is the difference between omega d and omega n? Iza Shamimi. What is the difference between omega d and omega n? Zeta is damping ratio. Iza Shamimi.
Yes, doctor.
Apa beza omega d and omega n?
Omega D
Omega
damping
omega
frequency
n. Omega n.
and damp natural frequency.
Omega d.
Damp natural frequency.
Okay. Itu beza dia Dam dengan omega dam. Dam dengan undam. Okay. So we can say that omega d also can be defined as omega n 1 minus square root zeta square. And then overshoot percentage, which is this one, please put OL, the symbol of OS, percentage. Okay. So when we remove the percentage, it will become OS, exponent, minus pi zeta, 1 minus zeta square. So no 100. So there is a different percentage overshoot and OS without percentage symbol. Do you understand? Do you understand, Muhammad Haikal?
Yes, doctor.
Okay. And then settling time is 4 divided by zeta omega n. So I can tell you that usually we make it easy. So this is the P omega D. This is real. Okay. Yeah. Okay. So J omega is equal to J omega B. This one is imaginary part. Okay. So we call it as imaginary part. Okay. Well, this one is minus is zeta omega n. Okay. So we call it as a real part. So we can write it TP as pi divided by imaginary part. Same. Okay. And then ds 4 divided by zeta omega n is equal to 4 divided by real. Okay, real magnitude of real, which is zeta omega n. Okay, so please remember this. Remember. Huh? Okay, we move to the next one, which is revisit the additional pole. So the formula will derive based on purely second order system. Therefore, the formula valid only for second order system without zero. Okay. However, under certain condition, a system with more than two poles can be approximate as a second order system. Yeah, let's say third order system. We can approximate it as a second order system when the third pole is far, far away from the imaginary axis. So in this case, the complex poles that dominate the overall performance are known as a dominant pole. Dominant pole meaning poles that have high influence towards the system output. Okay, towards the system output. So please remember dominant poles. Okay. Okay, we stop here. So we try to discuss the final exam question, the past year test one. I I already discussed with you. Give you in the WhatsApp. Okay. We continue the lecture next week, but the time remaining now, we try to do some revision for past year test one. Okay, so I invite Tan King Ying. Tan King Ying.
Yeah, doctor.
Can you please read the question for me? Because I have a cough.
Root locus of a unity feedback system is shown in figure Q.1. Based on the root locus shown in figure Q.1, determine the open loop transfer function GS of the unity feedback system.
Okay.
Estimate the imaginary axis JW closing points from the given root locus. Next, verify it by using appropriate analytical calculation. Estimate the breakaway or breaking point from the given root locus. Next, verify it by using appropriate analytical calculation. We determine the range of gain K that result in an underdamped system response.
Yeah. So plot is given, as I shown there, very clear, using Excel software. Okay, because MATLAB graphic not very good as Excel, so we can read there how many open loopholes there. Irfan, how many open loopholes?
3.
Huh? Berapa?
3.
3 open loopholes, 3, which is
-5, -2, and 0.
Yiling,
Hello.
open loop zeros, berapa?
2.
Which is
2 plus J1. 2 plus negative J1.
2 plus minus J1. So what is the transfer function? Ahmad Yosef.
Yes.
What is the transfer function? Open loop transfer function. Based on 3 open loop poles given and 2 open loop zeros.
Should I multiply
No, you
the
just
zeros each other?
give it to me now. S
Wait.
okay. Okay. Yosef.
Yes.
Yeah. 6.
Yes, now.
Okay, in front. Then multiply. Yosef. Multiply Yosef. Multiply.
S square minus 2s plus 1 plus 5 over s plus 2 s plus 5.
No, multiply all. Okay.
Okay.
And what is the open loop transfer function? Gn.
Yes, doctor.
Open loop. Closed loop transfer function. Closed loop.
1 the the upper one,
Okay. Okay.
and then divided by s cubed plus 7s squared plus 10s, and then the plus s squared minus 4s plus 5.
Okay. Ân Yi Yang.
Yes, doctor.
What is the characteristic equation?
Characteristic equation is the denominator of closed loop system transfer function equal to 0.
To the 0. Okay. Determine the opponent function of the unity feedback system. Finish. Estimate the imaginary axis crossing. Estimate from the given root locus. Then verify by using appropriate analytical calculations. Aulia Shadikin.
Doctor,
Yes, I.
for characteristic equation, it must be the denominator for closed loop, only closed loop, right?
Yeah, yeah. Denominator of the closed loop transfer function equal to 0. Okay?
Okay.
Okay. Aulia Sadiqin.
Yes, doctor. Yes, doctor. Hello.
Yeah, yeah. What is the J omega crossing point from the given plot?
Is it plus minus J 1.1?
Over here. Apa tu?
Yeah. J plus minus J 1.1.
J omega crossing point of the locus is plus minus
1.1.
1.1. So verify. How to verify whether 1.1 is correct or not?
Use the the table wait,
Table. Table apa?
the words look
Using Ruth Lewis table.
words hard with table.
What's about Ruth Lewis?
Words hard with table.
One more time.
Words hard with table.
Ruth Lewis table.
Words what?
Budak ni. Ruth
Huh?
Lewis table.
Words with table.
Ruth Lewis.
Betul.
Betul.
Okay, I got it.
S square. Eh. S cubic square. This one. Okay. So 1. Hmm. Farina Jaslin.
Yes, doctor.
This one.
4k squared plus 23k minus 70.
How you get it?
Using determinant.
And this one, Farina. The last one.
5k.
Wen Hui. Wen Hui.
Yes, doctor.
What is the theory of the Ruth Lewis criterion for stability?
What?
What is the theory behind
The
the
first column must greater or equals to 0.
okay, this one greater than 0, greater than 0, greater than 0, greater than 0. Okay. So 4k square plus 23k minus 70 equal to 0. Okay. So can you help me to find the roots? Akmal Hakimi.
Yes, doctor.
Find the roots.
2.2 and negative 7.95.
Yeah. So which one we choose?
2.2.
2.2, eh? So we choose 2.2 when we insert inside 7 plus k square. Okay. Plus minus j 1.1. Okay, cool. So what is the next question? The breakaway point or break-in point? Okay, so point over here. Is it a breakaway or break-in? Or in? Or in?
Yes, doctor.
Using your eyes, what is the estimation of the breakaway point or break-in point?
Negative 0.6.
Negative 0.6 estimate.
Yes.
Okay. Is it break-in point or breakaway point?
Breakaway point.
Breakaway point, yeah. Okay, breakaway point. So how to verify breakaway point using
Use differentiation.
differentiations. Okay. So d per ds, s square minus 4s plus 5 s cubic okay equal to 0. Okay, simplify. So you will get S4 okay, find the roots. Sharon Lau, find the root. Sharon,
9.58
positive.
positive,
Lagi,
negative 3.43,
lagi,
2.46,
lagi.
and negative 0.62,
So which one you choose?
negative 0.62,
Negative
62.
0.62.
Yeah.
Okay. Estimation 0 minus 0.6. Calculation minus 0.62. So which is acceptable. Okay. And then determine the range of gain K that results in the underdamped response. How to do it? Aikal? Aikal.
Hello.
How to do it? The last one.
Hello.
Yeah. D.
Ni kan doktor.
Hmm. Okay.
Value gain lah.
Ah.
Sekejap. 0.48.
K dia berapa?
K 2.2.
2.2. This one?
0.48.
6.
Eh,
Other one.
0.62. Oh, tu.
K dia berapa?
Ada range value of K kan?
Yeah.
0.48 to 2.2.
No, the K over here at the breakaway point.
Yep. K over here. Ni mana ni? Negative 0.62 lah.
That is the point.
Okay.
Point minus 0.62. Zeta value over there is 1. And what is the gain value? Gain.
Uh,
Uh,
0.48.
huh? 0.48.
48.
Okay. 0.48. So the range of stability is a range of gain K for under dam region is Michael
0.48 to 2.2.
Khairan.
Yes, doktor.
You know how to calculate 2.2? How you get 2.2?
No, doktor.
Huh?
2.2.
Ah. This one is from the root width. From the root width that you calculate. Can?
Yeah.
K critical. And how you calculate 0.48 Aina? How you get 0.48? How you get 0.48? Haikal tak tahu tu. Dia punya kawan dia gitu. Aina, tak datang.
Yeah, using
Oh, kat mana ni? Planet mana ni?
saya ada ni.
Ha? Marik?
Using the magnitude
Formula.
formula.
Ni kan?
Ah,
FSS tu berapa nilai dia?
apa dia doktor?
What is the value of K when we insert minus 0.62 inside these equations?
0.48.
0.48. Alright. Dah 1 jam. So, kita ambil attendance. Wait lah. Ambil attendance dulu. Faham tak? Saya ajar. Do you understand what I teach you?
Faham.
Yang lain tak dengar. Do you understand what I teach you?
Faham. Tapi laju.
Laju Laju. Tak boleh slow down lagi. Hanya sangat cuti. Okay, attendance Section 1 first. Get ready, section 1. Section 1. Section 1 dulu. Section 1 dulu. Scan. Section 2, get ready. Section 2. Okay, we'll delete this QR at 12 o'clock. Any question, guys? Any question? Hello?
No, doctor.
Okay, right.
Yes.
Thank you very much, and I'll see you next week, Tuesday, 10 p.m. Bye-bye.
Thank you,
Thank you,
doctor.
Doctor. Assalamualaikum.
Thank you, Doctor. Thank you, Doctor.
Thank you, Doctor.